All right, let's look at the next example. Example, find the point on the curve y equals x squared that is closest to the point 18 and 0. Okay, so this is a curve y equals x squared. Of course, the parabola. So this is the parabola here. Y equals x squared. And then we have a fixed point 18 and 0. Let's say this is 18 and 0. And we want to find the point on the parabola that is closest to this point. In other words, we want to have the distance between this fixed point 18 and 0 and the point on the parabola to be minimized. So this distance here, the point, basically, if you say that this is the closest point, let's say this point. Let's say this is point A and this is point B. So the point B on the parabola is the closest point to this point, fixed point A, 18 and 0. And we want to find this point B. Of course, we have infinitely many options for the point on the curve, but only one of them will be the closest point to A, right? So for example, if you compare B with, let's say, C here, or with D, for example, here, so see, B is closer than C and D, right? So among all infinitely many choices that we have for all points on the curve, this parabola, we want to choose the one that is closest to A. So basically, what is the expression or quantity that we want to minimize? So here we want to minimize the distance between A and point A. Remember, it's fixed point A, which is 18 and 0, and point B, let's say a point B on the curve, which can be written as x and f of x, which is going to be x and x squared in this case. Okay, so we want to find B. Want to find x, which will determine the point, right? Any point on the curve, on this curve, is of the form x and f of x. In this case, f of x is x squared. So any point on this curve is of the form x and x squared. Among all these points on the curve, we want to find the one that has the smallest distance to this fixed point A. Okay, so we said that we have to assign letters to the quantities that we want to find. Here we want to find the point, so we assign letter x to for the x coordinate of the point, and the y coordinate will be naturally x squared. And then we have to express the quantity that we want to minimize or maximize in terms of, or as a function of, one variable only. So now we have to write the distance between A and B as a function of one variable only. So the distance is square root of Distance between 2 points. You saw in high school or pre-calculus that distance between 2 points is square root of x2 minus x1 the whole squared plus y2 minus y1 the whole squared. So here it's going to be x minus 18 the whole squared plus x squared minus 0 the whole squared. X and 8x minus 18 the whole squared plus x squared minus 0 the whole squared. So then this is square root of x minus 18 the whole squared plus x to power 4. So we want to determine x. So this is already a function of one variable only. That's good. So this is a function of x. And now we have to find x that minimizes this expression. And before that, we have to also determine the domain of this function. So with domain, what is the domain of this function? Domain will be d equals minus infinity to infinity. Domain means x should come from what set? Well, x can be any number between minus infinity to infinity, because x is, the point can move along this curve, right? And as x moves along this curve, x can go anywhere from minus infinity to infinity. So domain of this function will be minus infinity to infinity, right? Because we want to choose among all points on this curve. We want to choose the one that's closest. All points on this curve means any point with x value anywhere from minus infinity to infinity. So again, domain is not closed finite interval, so it's not as straightforward as the problems that we had, a continuous function on a closed finite interval. But that's still okay, you know, we can still try to, or hope that we can find the absolute mean of this function. Okay, so we have a continuous function d of x equals square root of x minus 18 the whole squared plus x to power 4, and want to find absolute mean of this function, of course, if it exists. So let's look at the critical points for this function. So d prime of x, derivative of this function with respect to x, derivative of root u is u prime over 2 root u. So then this is going to be derivative of inside, which will be 4x cubed plus 2 times x minus 18 divided by, so u prime over 2 root u, so 2 root x minus 18 squared plus x to power 4. Now, if I set d prime equals 0, so first of all, d prime exists for every x, because the denominator, we have a denominator and it has a square root as well, but this expression is always positive because you have addition of 2 non-negative terms here. But these 2 non-negative, addition of 2 non-negative expressions is always non-negative, which means bigger than or equal to 0. But it cannot be 0, this expression, because this expression, if you look at the first term is 0 at 18, x equals 18. Second term, 0 at x equals 0. So these 2 terms cannot be 0 at the same time. So if one of them 0, the other one will be positive. And if the second one is 0, first one will be positive. So there is no possibility that the whole expression becomes 0. because both of them are non-negative. And if the first one is 0, second one is positive. If second one is 0, first one is positive. So we have a square root here where expression is positive. So this is always square root of a positive number. It's defined, and d prime will be some number in top over some number, some positive number in the bottom. So d prime of x exists always. So critical point means either a point where derivative does not exist or derivative equals 0. So derivative exists all the time for every x. So we just need to find the points where d prime is 0. So then that gives 4x cubed plus 2 times x minus 18 equals 0. And that will give me 4 4x cubed plus 2x minus 36 equals 0. If I divide by 2 everything, 2x cubed plus x minus 18 equals 0. Now this is a cubic equation. We don't have a simple formula to solve cubic equation like quadratic equations, but we can try to guess a solution. So for example, x equals 1, we can try. It's not a solution. X equals minus 1 is not a solution, but x equals 2 is a solution. So guess x equals 2 is a solution, because 2 times 2 cubed plus 2 minus 18 is equal to 0. So if x equals to a solution, that means x minus 2 is a factor. If x minus 2 is a factor, then we can find the other factor by doing long division, right? If you have a polynomial and you have one factor, you can do the long division to find the other factor, 2x cubed plus x minus 18. At 2x cubed plus x minus 18 equals x minus 2 times another factor. What should be the other factor? We can do the long division, or you can guess. So the first term should be 2x squared, because I need to get 2x cubed. So this should be x times 2x squared, which would give me 2x cubed. The constant term should be plus 9, because plus 9 times minus 2 will be minus 18. And the coefficient of x should be, how much should be coefficient of x? So I'm going to get 9x. See, how many x do we have in the right hand side? I have 9x plus this term here. So this should be plus 4x plus 4x, because plus 4x times 2 will be minus 8x, and plus 9x will be plus x. I'm trying to guess the middle coefficient here. This should be plus 4x, because times minus 2 will be minus 8x, plus 9x will be plus x. And the coefficient of x squared, which is 0 in the left hand side, should be automatically correct. Let's check. Minus 2 times 2 squared is minus 4x squared, plus 4x squared is 0x squared, which is consistent with the left hand side. So I found the second factor by guessing, basically. But if you're not comfortable with this, you can of course do the long division. So this is 2x cubed plus x minus 18 can be written as x minus 2 times this. Now if, or set 2x cubed plus x minus 18 equals 0, because this was the equation that we were trying to solve it. So then that means x minus 2 times 2x squared plus 4x plus 9 is 0. And that gives x equals 2 or 2x squared plus 4x plus 9 equals 0. But this one, you can easily check that this equation has no solution because the discriminant delta is b squared minus 4ac. That's going to be 16 minus 4 times 2 times 9, which is going to be negative. So I have only one solution. So only one critical point, x equals 2. Well, similar to previous example, when we have only one critical point, it suggests that we have either no local extremum or exactly one local extremum. So we will have either no local extremum or exactly one local extremum. To find out, either use first derivative test or second derivative test. Last question, last example, I use first derivative test and second derivative test. This time, let me use first derivative test. Let's use first derivative test. So see, these are the x values from minus infinity to infinity. We have only one critical point at 2, f prime here. And or f is the notation that I used for the original function x squared. Let me use d, which was the distance function, or d of x. So d prime of x and d of x here. So at 2, derivative became 0. Before 2, you can use a test point. And test point, let's say, for example, d prime of 1. See, d prime of x was this expression. If you replace x with 1, 4 plus 2 times minus 1 minus 18 is minus 17. 2 times minus 17 is minus 34 plus 4 negative. Denominator obviously positive, so the total answer will be negative. And then positive here, the function decreasing here, increasing here, and here we will have local minimum. So we have local minimum at x equals 2. Again, we can say that since we have exactly one local extremum, and this local extremum is a local minimum, so again, by theorem we saw last time, x equals 2 must be the absolute mean of d of x. Absolute mean of d of x. Okay, so that means, so what will be the point? The point was asking the question. So the point B with coordinate of B was x and x squared. X is 2, so 2 and 2 squared, which is 4, is the closest point on the graph of y cos x squared to the point A, 18 and 0. So only the point on the curve was asked, and the point is 2 and 4. Now, if the the distance, if the actual distance is also asked, we can easily find it because we have both points, we can find the distance. That distance will be the minimum possible distance between A and the point on the curve. But right now, only the point on the curve is asked, and the point on the curve, which is closest to A, is 2 and 4. Okay. Okay, guys. So the last topic I want to mention here is about Newton's method, which is a method to approximate the root or roots of a differentiable function. Differentiable function f of x. Okay. So finding roots of functions is always an important problem in mathematics. Previously, we saw one method, how to approximate the root of a function, which was using intermediate value theorem. So previously, we saw how to estimate a root, root of a function, of a continuous function, basically. Previously, our only assumption was continuity of f, but in Newton's method, we need to also assume differentiability of f. How to estimate the root of a continuous function f of x using IVT, intermediate value theorem. So we saw that if f of A times f of B is negative and f of x is a continuous function, then f of x must have a root between A and B. So for example, f of -1 times f of 4 is negative. That means the function has a root between -1 and 4. And we could improve the accuracy. We explained before that we have to cut the interval into 2 halves, and then let's say if the middle point is, let's say, C, then you see f of C times f of A is negative, or f of C times f of B is negative. Then you can improve the accuracy. We have explained this before. Now, this is another method, okay? So problems in mathematics in many situations have different approaches or different solutions. So one approach was using IVT. Now here we want to use another approach, okay? So in Newton's method, to estimate a root, start with an initial estimation, say x equals x1, which can be found using IVT. Just start with some initial estimation. Your initial estimation, for example, could be based on IVT or any other method. We need an initial estimation. It doesn't have to be very accurate, okay? So just a very rough estimation is okay. Ultimately, we will get a good accuracy when you use Newton's method. So let's look at the graph of a function, and let's say if I start the initial estimation for my root. Let's see what happens. Let's say this is a differentiable function, and I start with some initial estimation x1. See, this is my root here. My root, let's say I call it, for example, R. See, x1 is the initial estimation for R. Now, the next level or next step, we want to have better estimation. Next step, we want to improve this estimation. How can I improve it? To do so, consider the tangent line at x equals x1 to y equals f of x, and consider the x-intercept of this line. You see, this is the tangent line. At x equals x1, and x-intercept of this line, look at here. X-intercept of this line, if I call it x2, is a better estimation for R because x2 is closer to R compared to x1. There is less error when I consider x2 for estimation of R rather than x1. So x2 is a better estimation for R. And what is x2? Well, x2 is the x-intercept of which line? The tangent line at x1. What is the tangent line at x1? Y minus f of x1 equals f prime of x1 times x minus x1. So if I replace y with 0, then we get minus f of x1 equals f prime of x1 times x minus x1. And then if I just need to solve for x, right? To find x-intercept of a line, you learned in high school. You replace y with 0 and you find the x value. So I did that. I replaced y with 0. I'm finding x value. So then that gives me minus f of x1 over f prime of x1 equals x minus x1. So then x is equal to x1 minus f of x1 divided by f prime of x1. So I can say that x2 is equal to x1 minus f of x1 divided by f prime of x1. In the next step, improve our estimation. Similarly, what do I mean? I mean that, again, consider the tangent line at x2 this time. This is tangent line at x2. See? Tangent line at x2, and then I need to consider the x-intercept of this line, which I can call it x3. So again, x3 will be x-intercept of tangent line at x equals x2, and x equals x2 will be what is it? Y minus f of x2 equals f prime of x2 times x minus x2. And for tangent, for x-intercept, I need to replace y with 0. Again, I get minus f of x2 equals f prime of x2 times x minus x2. And a similar calculation to what we did above. It tells us that x equals x3 equals x2 minus f of x2 divided by f prime of x2. So continuing this process, we can see that xn plus 1 is equal to xn minus f of xn divided by f prime of xn. So this is called Newton's method. Newton's method formula. So in Newton's method formula, you start with some initial estimation x1, then you can improve your estimation and find x2. How do we find x2? x2 can be found using x1. x2 will be x1 minus f of x1 or f prime of x1. Once you have x2, you can find x3. How do we find x3? Again, using the same formula. x3 will be, it will be found using x2. x3 will be x2 minus f of x2 over f prime of x2. Once you have x3, you can find x4. And so on. So this is called a recursive relation. Called a recursive relation. Recursive relation means a relation that you find one term in terms of previous ones. We find xn plus 1 in terms of xn. So if we find x2 in terms of x1, once we have x2, we can find x3 in terms of x2. Once we have x3, we can find x4 in terms of x3, and so on. All right, let's look at an example. Use the Newton's method. Use Newton's method to estimate the real solution of x cubed minus x minus 1 equals 0. So first of all, you can check that this equation has only one root. This is a cubic equation, but this equation has only one root. For example, you can sketch the graph of this function and show that it has one real root, or you can do this with other methods. So maybe I can leave that as an exercise. Show that x cubed minus x minus 1 equals 0 has exactly one root. There was a question in the exam actually as well that was asking you to show that some given equation has exactly one root. So do this as an exercise, has exactly one root, say x equals r. So we want to estimate x equals r. How can we do that? So we have to start the initial estimation. Start with an initial estimation. So initial estimation, we said we can find it by using IVT. So let's say f of x equals x cubed minus x minus 1. And then let's say f of 1 times f of, we can say f of 1 times f of 2 here. F of 1 is minus 1 times f of 2 is 5. Right? And this is negative. and f of x is continuous. So by IVT, we can say that there exists a root between 1 and 2. Let's use x equals 1.5 as our initial estimation. I use the middle point as the initial estimation. You don't have to. You can use 1.4, for example, as the initial estimation. We just know that there is a root between 1 and 2. Now, it doesn't have to be in the middle. So we just use the middle point, but you can use 1.4, 1.6, 1.7, any point between 1 and 2 as your initial estimation. So the initial estimation, we call it x1, if you remember. So let's call it x1. And then once we have x1, we can find the remaining. So now next to find x2, x2 means an improvement of x1, right? We start with some initial estimation, then we improve it to x2, then improve it to x3, and so on. Next, to find x2, how should we do it? With this Newton's method formula. This Newton's method formula gives us any xn plus 1 in terms of previous one xn. So it gives us x2 in terms of x1, x3 in terms of x2, and so on. So let me call this one maybe 2 star. So use, to find x2, use 2 star above. So x2 is equal to x1 minus f of x1 divided by f prime of x1. So that's going to be x1 minus f of x1. F of x is x cubed minus x minus 1. So x1 cubed minus x1 minus 1. F prime of x1, 3x1 squared minus 1. And then this is going to be 1.5 minus 1.5 cubed minus 1.5 minus 1 divided by 3 times 1.5 squared minus 1. And if we do the calculation here, we will get 1.3478269. Right? F of x was given to us in the question. Therefore, f prime of x, f of x was x cubed minus x minus 1. F prime of x will be, of course, 3x squared minus 1. And here we need f of x1 divided by f prime of x1. So that's how we wrote it. And x1 was 1.5. We replaced x1 1.5. This is the number we got. Okay, now how do we know when to stop? Well, let's say if the question asks us to find or estimate the solution, let's say up to 8 decimals. Let's say I want to estimate the solution up to 8 decimals. Right now we have this estimation, x2. Now let's continue our process. So x3 is x2 minus f of x2 over f prime of x2. So if we do the calculation, this will be almost equal to 1.32520040. Now if we continue, then x4 will be almost equal to 1.32471817. x5 almost equal to 1.32471796. x6 almost equal to 1.32471796. So x5 and x6 are the same number up to 8 decimals. So these are the same up to 8 decimals. So that means the root up to 8 decimal is the same number actually. So the root up to 8 decimal is 1.32471796. So if we found two numbers, both of them are the same up to eight decimals, that means our estimation right now is accurate up to 8 decimals. So x6 and x5, what is the difference between them? Well, the difference is after 8 decimals. Up to 8 decimals are this, they are the same, which means that the root is also this is the same up to 8 decimals. But x6 still is an improvement of x5 because the correction happens after 8 decimal, maybe in the 9th decimal or 10th decimal and so on. But x5 and x6 are the same up to 8 decimals. So these two are the same, and the root is also the same as these two up to 8 decimals. Okay. Now the next example. The equation cos x equals x has a solution between 0 and 1 and use Newton's method to approximate it. Okay, we want to find the solution of cos x equals x, the solution that lies between 0 and 1. Or we can also verify ourselves that this has a solution between 0 and 1. Right now, the question says that we can assume that it has a solution between 0 and 1. But even if it doesn't, we can find out by ourselves that it has a solution between 0 and 1. Because if I set my function, let's say f of x equals cos x minus x, we want to find the root of f of x. Okay, and we already know that if f of 0 times f of 1 is negative, then since f is continuous, it means that f must have a root between 0 and 1. And we can easily check that f of 0 times f of 1 is negative. So it must have a root between 0 and 1. So that's why I was saying that we could conclude ourselves that this has a root between 0 and 1. But right now the question actually gives us this information and tells us that we can assume that this is true. And by the way, here everything is in radians. So when I say f of 0 and f of 1, if you want to find cos 1 radian, by cos 1 mean cos 1 radian. If you want to use a calculator, use the radian. So we want to find the root of f of x. So it says that the root is between 0 and 1. And remember, we need an initial estimation. Initial estimation could be anything. So let's say I could use, I can use a number between 0 and 1, or 0 and 1 themselves as well are okay as well. Okay, so initial estimation, as you can see, as you can guess from the name, it's just initial estimation. It doesn't have to be accurate. Even if it's not accurate, you will converge to the real exact value of the root very fast according to this method. So let's use, for example, 1 as the initial estimation. Let's use x1 equals 1 as our initial estimation. Then x2 will be what? x1 minus f of x1 divided by f prime of x1. Remember the Newton's method formula, xn plus 1 is xn minus f of xn over f prime of xn. So that's going to be 1 minus f of xn means cos 1 minus 1 divided by f prime of xn. What is f prime of xn? F of x is cos x minus x. So f prime of x is minus sine x minus 1. So minus sine 1 minus 1. You can see that this value is almost equal to 0.7530 63868. And then, or next, we can say that x3 is x2 minus f of x2 over f prime of x2. So you do the calculation, you'll see that this is almost equal to 0.739112891. So again, how do we know when to stop? Again, you have to look at the question. Let's say if the question asks us to estimate up to, let's say estimate up to 9 decimals, for example. So that means we have to continue until 2 consecutive estimations are actually the same up to 9 decimals. Then that means the root is also the same up to those 9 decimals. So again, continuing this process, then x4 will be almost equal to 0.739085133, and x5 is almost equal to 0.739085133. So these two are the same up to 9 decimals. So that means the root is 0.739085133 up to 9 decimals. Okay, so I want you to notice that, this method is much faster and more efficient than using IVT for estimating the roots. If you remember, for IVT, we could also estimate the roots, but, we had to consider half of the interval. And then let's say if you call it, for example, C, then you have to say f of C times f of A is negative, or f of C times f of B is negative. Then again, you will find the new subinterval, again in the new subinterval, a midpoint of it, and then f of, let's say, D times f of C is negative. Or so the calculus, it will include so much more calculations, and you will have, even if you remember, even for estimating up to 2 decimals, for example, it took a lot of time and more calculations compared to this. So maybe I can mention here that as a remark, that this method is faster, more efficient, with less calculations. It's faster to estimate the root of a function of a differentiable function compared to the method we learned before using IVT. In mathematics and also in computer science, it's important that when you want to create or construct an algorithm, what is the complexity of it? How many computations or calculations are needed to perform a specific task or a specific algorithm? It's very important, especially in computer science, it's very important. So this is a simple example that both these methods estimate the roots, but this method, Newton's method, is faster, more efficient, and with less number of calculations. So one more remark that I want to mention here is, although Newton's method can be applied in most cases to estimate the root or roots of differentiable functions, there are, unfortunately, some exceptions. Some exceptions where Newton's method stops working. In most cases, you can apply it. As long as you have a differentiable function, you can apply it to estimate the root. Very fast and very efficient. But some exceptions, in rare cases, it cannot be applied. For example, if f prime of xi is equal to 0 for some xi, then Newton's method cannot be applied to find the next step estimation xi plus 1. We know that, remember the Newton's formula, Newton's method formula, xi plus 1 or xn plus 1 is xn minus f of xn or f over f prime of xn. Now, if for some I, f prime of xi is 0, of course, we cannot divide by 0. So we cannot find xi plus 1 because xi plus 1 is supposed to be xi minus f of xi over f prime of xi. If f prime of xi is 0, then we cannot find xi plus 1. So that's one case where Newton's method stops working. Or in another example, let's say if I set f of x equals x to power 1 over 3, then f of x has the root x equals 0. Now let's use, if we use the initial estimation x1 equals 1, then what do we know about x2? x2 will be x1 minus f of x1 over f prime of x1. So that's going to be 1 minus f of x1 is 1 over f prime of x1, derivative of this function is 1 over 3 x to the power minus 2/3. So maybe first I can write it in terms of x1. This is x1 minus x1 to the power 1 over 3 over 1 over 3 x1 to the power minus 2 over 3. So that's x1 minus 3 times x1. because x1 to the power minus 2 over 3 is in denominator. If you take it to the top, it becomes x1 to the power 2 over 3 times x1 to the power 1 over 3. That will be x1. So x1 minus 3x1 is minus 2x1. So x2 would be, if x1 is 1, x2 would be minus 2. And therefore x3 would be minus, similarly, minus 2x2, because we can, the same calculation that we did here will hold for x3. So this was x2 in terms of x1. Similarly, x3 in terms of x2 would be minus 2x2. So that's going to be, if x2 is minus 2, that's going to be minus 2 times minus 2, which is 4. x4 would be minus 2 times that guy, minus 8. x5, minus 2 times that guy, 16. So xn is going to be not convergent to x equals 0. Not convergent to x equals 0 means xn, the values of xn do not get closer and closer to 0 as n gets larger and larger. So that's what we want. We want xn, the values of xn, to get closer and closer to the root as n gets larger and larger. This was the case in the previous examples. X1, we started with 1, then x2 some decimals, x3 some decimals. Those get closer and closer to the root. And that's why Newton's method can be applied in general. But in some rare cases, for example, this one, look at the values of xn. The root is 0. The root of, this is a simple function, cube root x. The root is 0. But what are the values of xn? If I start with x1, 1, then it's minus 2, then 4, then minus 8, then 16, and so on. So of course, they will not get closer and closer to 0. In fact, they're getting farther and farther from 0. The first one is 1, then minus 2, then 4, then minus 8, and so on. Okay, so Newton's method stops working in this example as well, although f prime is not 0. So we saw that in one case that Newton's method stops working is if f prime of xi is 0 for some xi. Another example is this: f prime is not 0 for any of xi's, but still Newton's method does not work because it does not give us an estimation for a root and the values of xn. Rather than getting closer and closer to the root, they are getting farther and farther from the root. So, but you could ask why this function doesn't work. Which functions? We know that for most functions, they're okay. We can use Newton's method to estimate their roots, but some rare functions, no, we can't use. Now, which functions? For which functions we can't use Newton's method? That's the question. And the answer of this question, we don't want to study in this course. In a higher level course or numerical analysis course, you can learn for which functions Newton's method stops working. So to characterize functions for which Newton's method stops working, take a numerical analysis course. Usually third year level numerical analysis, third year level course. In that course, you can learn exactly which functions, for which functions Newton's method stops working. Okay, guys. So that's it. This was Calculus 1, Math 113, Calculus 1, or Differential Calculus course. So thank you for watching all these lectures, and hope to see you soon. Bye.